Hello, welcome to today's session of organic chemistry. So let's briefly talk about the kind of reaction that we mentioned during our last session. So during our last session, I talked to you guys briefly about the three different kind of organic reaction that we'll encounter in our first year of IB chemistry. And those reactions were free radical substitution reactions for alkanes, electrophilic addition reaction for alkenes and alkynes, and nucleophilic substitution reaction for alcohols and haloalkanes. We went into detail about the free radical substitution reactions, taking an example of a methane and chlorine reactions. Okay, in today's session, we'll be talking about electrophilic addition reaction that happens in alkenes and alkynes. Okay, so let's get started. So we're going to mainly focus on alkenes because alkynes is sort of out of the scope of this course. But I might do a different session for the alkynes later on. But for now, let's focus on alkenes. So alkenes are unsaturated, unlike alkanes. That's why they undergo addition reactions. Okay, they are unsaturated. They have double bonds. They have delocalized pi electron. As a result, they can take in more stuff. They can form more bonds. That's why they undergo addition reaction. Specifically, we are going to talk about electrophilic addition reaction, where the key requirement is an electrophilic source, electron-loving group. Okay, that would initiate the reaction because you have electron in your alkenes, you have pi electron in your alkenes. So as long as you have the electrophilic source, the electrophilic addition reaction will be initiated. And of course, you'll need an alkene substrate as well, the alkene molecule. So whenever you have electrophilic source and alkene molecule, the electrophilic addition reactions are good to go. Okay, and I've sort of split the electrophilic addition reaction in alkenes in three different categories based on the mechanistic pathway, based on the kind of mechanism that these reactions go through. We can sort of classify this reaction into three categories. The first category is where the reaction goes through a formation of carbocation. Okay, a positively charged carbon center is a carbocation. So we'll call that the Carbocadon pathway. This happens when you are adding haloacids like HBr, HCl, HI, hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay, iodic acid. And this reaction is called hydrohalogenation reaction because you are adding a H and you are also adding a halogen atom. HCl, which is a combination of H and Cl. So that's hydrohalogenation, and that occurs via the formation of carbocations. So we will call those electrophilic addition reaction, the Carbocadon pathway reactions. The second category is the three-membered ring pathway. These reactions will proceed via the formation of a three-membered ring, which is the transition state, or like the intermediate, let's say specifically intermediate. And this happens when you are adding halogen molecule, not haloacids, not HBr, not HCl, not HI. You are adding halogen molecules like Br2, Cl2, I2, and those reactions are called halogenation. Whenever you are adding a halogen molecule onto an alkene, the reactions are called halogenation reaction. And halogenation reactions on alkene occur via the formation of three-membered ring. Okay, so that's the second category of reaction. The third category of reaction is the concerted pathway reaction. Okay, so this happens when you are adding a hydrogen gas, hydrogen molecule on alkene. Okay, which is not possible in a normal room temperature situation. You need catalyst. Usually we use catalysts like platinum, palladium, even nickel to undergo this reaction, and this reaction go through this concerted pathway. That's why we put this reaction in this third category. Okay, so we'll talk about these three different mechanisms of electrophilic addition reaction in alkanes. Key requirements, of course, I said there should be an electrophilic source. In the case of haloacids, the HBr, HCl, and HI, they would act as an electrophilic source, providing that electron-loving group. In the case of three-membered ring pathway, you'll have halogen molecules, Cl2, Br2, I2. Those will behave as electrophilic source. In the concerted pathway, you'll have a hydrogen molecule, H2 gas, right? That would behave as a source of electrophile. Okay, so let's get started. The first one, the Carbocadon pathway. What I'm going to do first is I'm going to give you like a general mechanism for all those three different pathways. And in the next session, we'll take specific molecules and a specific reaction and go into detail and maybe even draw arrow diagrams, okay, on a whiteboard. Okay, let's, so on the carbocadon pathway, like I told you, you should have an alkene. So this is an example of an alkene. You can see, let's, if we have to name this alkene, it's a 1, 2, 3, 4 carbon chain. It's a butene. It's a 2-butene, but also there are 2 methyl group coming off from the second and third carbons. So it would be 2,3-dimethyl butene. Okay, 2,3-dimethyl 2-butene. That's the alkene we have. And our electrophilic source are HBr, HCl, and HI, because I told you before the carbocadon pathway works for HBr, HCl, and HI whenever you are adding haloacids. These are haloacids, and the reaction is called hydrohalogenation reaction. And specifically in this haloacid, the H plus part, right? Because if you break down the HBr, it's H plus and Br minus. The H plus is the source of electrophile. Okay, so in the first step, the pi electrons, the electrons sort of like the reservoir, would attack the H plus, and then you'll form, we can call it X for now. This X plus is basically the H plus. Will form a bond with this carbon here, so you form a new bond. As a result, this carbon, the carbon on the right, will get a positive charge. So that's a carbocation. That's the intermediate that I was talking about. That's why this pathway is called carbocadon pathway, because it occurred with the formation of carbocation. Now in the second step, the positive charge carbon center will bond to the nucleophile, the negative part. Remember, if you break down the HBr, you get H plus, but there is also a Br minus on your reaction mixture. So that Br minus will bond to the carbon, the positively charged carbon. As a result, it will form that CBr bond, or carbon halogen bond. So at the end, you have this di-substituted alkane. Okay, so it's a hydrohalogenation reaction that occurred with the formation of carbocadon intermediate. There's a little note that I put here. This type of reactions are a combination of syn and anti-addition. So I'd want you to know actually what syn addition and anti-addition mean. So what happens is, now see here, let's go to this intermediate. Okay, at the end of the first step, you are forming this carbocation. And if you remember our VSEPR class, whenever you have a 3 electron groups around an atom, the structure of that center would be a trigonal planar. It's a planar center. It's actually a flat center right here, 2-dimensional. So whenever this Y minus comes and attacks this carbon, it can come from the top or from the bottom, right? It has that free choice. It can attack this carbon from the top or from the bottom because it's a flat center here. It's a 2-dimensional center. So after the attack, if the Y positions itself so that it's on the same face as the X, if both X and Y happen to be on the same face at the end of the reaction, that kind of addition is called syn addition. Okay, but if the Y minus attacks from the opposite side of where the X is, then at the end, the X and Y would be in the opposite side, right? X would be on the top, Y would be on the bottom, if you consider this to be like a reference line. And that type of addition is called anti-addition. Anti means opposite, syn means similar. Okay, just remember, in case of carbocadon pathway, whenever you are adding a haloacids to an alkene, the final mixture will be a mixture of syn and anti product. Okay, this is the general mechanism. So let's go to the second one, the 3-membered ring pathway. So this happens whenever you are adding halogen molecule, not haloacids, halogen molecule on alkene. Okay, so the source of electrophile would be halogen in this case, halogen molecule, one of the halogen atom, and substrate is that alkene, is your alkene. Okay, and this is also called, if you go back to the first slide, or the second slide actually, this is also called halogenation reaction. Addition of halogens, halogenation reaction occur with the formation of 3-membered ring. Okay, so let's go here. So what happens in the first step is this pi electrons, the delocalized free pi electrons, would actually repel the electron cloud that's present around this halogen molecule. As a result, this halogen atom would be partially positively charged, and this halogen atom would be partially negative charged. Okay, so now once you have a partially positively charged center, the electron, the pi electron, would basically make a bond here, right? and this thing would go away as X minus. But remember, now if you go back to the slide before, in our previous slide, what we had was the X would make that bond with the carbon and you'll have a positively charged center here, carbocation. But now the difference is this X is not going to make one complete bond with one of the carbons and leave the other carbon as positive. That's not going to happen. What's going to happen is the X is going to stay somewhere on the center and be affiliated to both of this carbon and make this nice looking three-membered ring, which is called halonium ion. Okay, if it's a bromine molecule, we call this bromonium ion. If it's a chlorine molecule, we call this chloronium ion. If it's an iodine molecule, we call this iodinium ion. We are not going to deal with notoriously active fluorine, so fluorine is out of scope. We only deal with bromine, chlorine, and iodine. Okay, so remember, whenever you are adding a halogen molecule to an alkene while doing the halogenation reaction in alkene, it occurs via the formation of halonium ion, not the carbocation. Okay, so the X, one of the halogen atom, would sit right on the center and bond with both of this carbon and have a positive charge, because halogen don't make two bonds. Whenever they make two bonds, their charge becomes positive, and you'll have a negatively charged X, which is basically the other half of this guy, this molecule, right? That's the first step, formation of halonium ion, very important. On the second step, the negatively charged halide, or the nucleophile you can call it, would attack one of this carbon, right, and form a bond with the carbon here, and this electron, one of this bond, electron in this bond, would move to the X plus and make it X neutral. Okay, there should be one more arrow here actually. Add one. So the first is the X minus would attack one of the carbon and form this carbon X bond, and either take this pair of electron or this pair of electron and put it back to the X, and you get the CX, right? Well, I guess if you attack this carbon, then this X would be bonded to this carbon, but if you attack the carbon on the left, then X would be bonded to this carbon. As a result, you get this vicinal dihalide. Vicinal meaning the two X's would be attached to the adjacent carbon, not on the same carbon, okay? That's what I was saying earlier. If the X attacks the carbon on the right, then the X on the top goes to the carbon on the left. If X attacks the carbon on the left, then the X on the top goes to the right carbon, okay? That's the three-membered ring pathway whenever you are adding halogen on alkene. Here, it's not going to form syn product, it's going to form anti-product, and you can see why. In this reaction before, this carbon, positively charged carbon center, was free to be attacked from the top or the bottom. Now, the difference is here, the top part is blocked. Interesting, right? The top part is blocked because of this three-membered ring. As a result, this X minus has to go from the bottom. As a result, you'll form this anti-product. The X on the top and the two X's are on the opposite face or the opposite side of this carbon-carbon bond. And that's called the anti-addition, the anti-product. And this dihalide, because it has two halogen atoms, is called vicinal because the two halogen atoms are attached to the adjacent carbon and not the same carbon. Okay? That's the three-membered ring pathway. Now let's go to the third one, the concerted pathway, right? If you go back to our summary slide, the concerted pathway happens whenever you are adding a hydrogen molecule over an alkene in the presence of catalyst. This reaction requires catalyst because the hydrogen molecule is pretty stable and you need catalyst in order to break that hydrogen-hydrogen bond. Okay, so the concerted pathway happens whenever you are adding a hydrogen molecule on an alkene, and those reactions are also called catalytic hydrogenation. Let's go to the reaction. So what happens is, this is a very interesting reaction. So this is the metal catalyst I was talking about. It could be platinum, it could be palladium, it could be nickel, usually mixed with carbon. It's a solid substrate or solid platform. And what happens is the hydrogen-hydrogen bond breaks down only in the presence of this metal catalyst. That's the important part. The metal catalyst, the interaction between the metal catalyst and the hydrogen molecules helps in the breakage of this hydrogen-hydrogen bond. As a result, you'll have a lot of free hydrogen atoms pretty reactive hydrogen atoms available in the reaction mixture. That's the first function of the metal catalyst surface. The second part, the alkene also finds this nice flat foundation to rest. Okay, the pi electrons here interact with the metal surface, and the alkene sort of rest on this solid platform. That's very important, first part. Now in the second part, this hydrogen now slowly starts to interact with this carbon. Or you can say the electron here starts to form bond with the hydrogen, whatever way you want to go, right? And you form a CH bond here. Okay, that's shown here. So first CH bond is formed. Similarly, the second carbon atom also gets the chance to interact with the other hydrogen atom that's lying around, or the floating around, let's say. So we'll form that second CH bond. At the end, you'll have an alkane. You started from an alkene, now you added two hydrogens. You basically made two carbon hydrogen bonds and got an alkane. Okay, this kind of reactions, this kind of pathway of hydrogen addition on alkene is called the concerted pathway. And if you look at the product, in this case, it's going to be all syn product, because both of these hydrogen atoms, this one and the orange one, are going to attack from the same face. It's pretty clear from the picture itself. Both of these hydrogen atoms are going to attack from the same face, are going to be attached to the same face. As a result, you'll get a syn addition product. Okay, so that's the concerted pathway. Happens when you are adding hydrogen molecule on an alkene. So that's pretty much the three kind of mechanistic pathway that the electrophilic addition reaction in alkenes goes through. Carbocadon pathway first. This happens for halo acids, HBr, HCl, and HI. The reaction is called hydrohalogenation reaction. The three-member ring pathway, whenever you are adding halogens, chlorine, bromine, and iodine onto alkenes, the reaction is called halogenation. And the third pathway is the concerted pathway. This happens when you are adding a hydrogen molecule to an alkene in the presence of a catalyst. Okay, so that's it for now. In our next session, we are going to take specific examples of these three different pathways. Okay, we'll take specific molecules, specific electrophiles, and do the detailed analysis of the mechanism. Okay, so yeah, thank you very much. I'll see you guys soon.